could.
The only other ones that would work for me are the 12 to 3 ones. Like this one.
I could do the Tuesday.
No. The only two that work for me are probably this one definitely works, but there's other stuff I want to do at the same time. So I'm not
Technically, I could do the Thursday one. I would just have to change which each 3
let's do whatever this weekend. Then by like the weekend I'll know for sure.
Okay.
Because I would actually do it with you.
It'd be nice to what?
To do it with you rather.
Yeah, I agree. That's yeah. I'm also gonna. I'll just drop a message in the Radiate Slack and ask if anyone's able to take that lab, just in case. Yeah.
I should be confirmed in like a day or two.
Also, this all hinges on finding someone to switch into.
Right. I don't know how to do that.
Yeah.
I'm gonna make a piazza post like maybe tonight or tomorrow.
Well, would you rather me make a Piazza post to switch into yours, or you make a Piazza post?
We can both make it.
But then it just matches to each other.
We won't respond to each other. That's hilarious. Wait, so you 12 to 3 ones for you though?
Not really. No, I have a lecture.
Hello, hello.
I mean, my 43 lecture.
Yeah.
Are you guys able to hear me on the way back? Are you able to hear me? Good. Okay. All right, guys. Let's about to get the lecture started. So this was from the previous lecture, and it's due by the end of today. Please try to fill out this form, whether you are currently enrolled already or you are trying to get into the class. So we are working together right now to get more seats into the class. We're probably going to have additional 18 to 20 seats to the class. So if you're on the wait list and you are like reasonably ahead, chances would be pretty high. The most likely the additional lab section is going to be on Friday. So if you want to do some, just think about if you're on waiting list. So today's lecture, we're going to talk about the instruction set architecture. A little bit announcement. Logistic-wise, class website, if you still haven't checked it out, please do. On the lecture schedules, homeworks, and everything related to the class will be posted on this website. And then Piazza is the first place to ask questions. We do not use the Canvas, unfortunately, but all the lecture-related stuff, slides, lecture recordings, homework assignment, labs, and stuff can be all found on the class website. Assignment-wise, homework 1 posted yesterday, and then it's due on Friday. Technically, if after today's lecture, you should be able to finish most of the homework 1. So hopefully that's not too much of a burden. I understand that the deadline is short, but the class is pretty packed across the semester, as you will learn by yourself. So yeah, for lab 1, how many of you already checked out your lab sections? Who already done the labs? Nice. How was it? Okay-ish. Okay, that's not bad. So as we said before, normally the pre-lab is due before your lab sections. This week only, it will be due during your lab sections. And for those who are on the wait list, you can try just go to the lab sections that you originally on the wait list for. We'll try to get you the lab kit and then work way through with you to hopefully get all of you guys or most of the people on the wait list into the class in the end. Office hours on Wednesday at my office, 12 p.m. to 1 p.m. And if you check out the class website, not sure if you did, but let me just show it. So if you go to the labs here, you will see that all the lab sections, currently the lab sections are on, and then all the open labs you see, they're pretty much also like office hours that for homework questions, lab materials, and maybe later on, probably later on for your final project as well. So let me get that out of the way. Cool. Any questions around the class logistics, the way we present the materials and everything? Anything? Okay, perfect. So a little bit recap from last lecture. We did like a class overview, discussed a little bit about what the embedded system is, and where hopefully give a prediction on where it's going to, as well as we talk about the high-level ARM system architectures plus the GPL, and just give you a little bit more recap. This is what like a GPL internally looks like. On the top, it's the input side, and the bottom is the output side. So it can be both input and output, and it's being controlled by additional registers from the core, so to let you know that which current mode the GPL is set to. On the bottom right here, that little M1, M2 thing, that's just a pull-push pair. You can think of them as like fancier switches in switching different modes. These type of switches allow basically more current passes through compared to normal switches that you work with. And for the next couple of weeks, the goal here is for you guys to understand how the code in our specific case, the ISAs, instruction sets, memories, and registers working together. And how does the microcontroller interact with outside of the board, outside of the core from its perspective through the MMIO system, memory mapped in and out. For the lecture today, we're going to first briefly talk about the background in ARM, and then talk about like the instruction set architecture, ISAs, the memory register, a little bit on the data width, 16-bit, 32 bits, etc. A little bit on the, more on the instruction, specifically some instruction encoding, different types of instructions, and then we talk a little bit on specifically the move, load, stores, and a little bit of the flow control. So for those who take 370, some of these materials might seem familiar to you, which is okay. The material will still get unfamiliar to you, so stay with us. And if we had time, we have like one indexing problem to just look at together, but we might not get to that. But we will release the questions and the answers in the slides is released after the lecture. So yeah. Cool, let's start with background in ARM. So what is ARM, or like what's the ARM's business model? Basically, well, technically, it doesn't produce any of the chips. It's a fabless semiconductor company. What does that mean? So basically, it doesn't really make any physical IC chips, but instead they create these architectures and instruction sets and then wrap them as IPs for the actual hardware manufacturers to match the chips that using their instruction set and way of interacting. And these are just some of the examples that, and different type of chips from different companies that made based on the ARM. So any guesses on why don't they make their own chip? Obviously, there are like a lot of reasons. Common reasons we usually refer to is because it's hardware, it's hard to make, and it's gonna be having like some small bugs here and there that leads to just a lot of hassle. And from like a fabless, or like if you just do like instruction sets, etc., it makes it much easier to treat those from like a more program perspectives rather than those nitty-bitty hardware implementations. Also, if you noticed, when like the Apple iPhone chips is also based on the ARM architecture. It's for some of these bigger companies, they do like more major modifications. So whatever they use is still ARM-based, but they're like heavily modified. So might not be standard ARM ISAs. Give a little bit more detail on these. They have typically have different families. The Cortex-A family usually are the ones that with like a screen on. The Apple chip, they usually call it like A something, right? So that's based on the Cortex-A family. The Cortex-R family stands for real-time. It's usually optimized for like high reliability type of applications. For example, like transportations, like those control systems on your cars, flights, etc. You don't want them to fail. And then the Cortex-M family, which is what we're going to mainly be focusing on. The M stands for microcontroller, usually lower power and more cost sensitive. And it's more like everything. So a lot of these devices you see around you are usually based on the M family. A lot of them nowadays actually also have like system on chip, so some of them have like small operating systems on them as well, but they are generally just Cortex M family. And give you a little bit information on the architecture versus the instruction set. So they are different. On the top, you can see are the different type of architectures. So we have like ARM v4, v5, v7, and the bottom there is the instruction set. So they don't usually 100% one-to-one mapping. Some of the instruction set can be used for multiple architectures. For our course specifically, we will be looking at the ARM v7 architecture, which is what the Cortex M4 is based on, also M3 and a few other things. And the instruction set we'll be working with, it's this thumb2. So notice that thumb2 was certain type of thumb2. Thumb2-2 mixed ISA is also compatible with the ARM v6 and ARM v7 on the left side. So technically, our instruction set can control some of the iPhones, technically. But what is the instruction set architecture, or ISA? It's pretty much like an agreement that between the programmers and hardware. So basically, let me just get all those out. So that if you use these instructions, the corresponding hardware is going to be doing exactly what is instructed or saved to do. So typically the ISA, the instruction set architecture, defines the different type of instructions, add, subtract, move, load, and it contains information of different data type. Is it a word, string, hard word, signed, unsigned, as well as how data storage, how the address is being assigned, or like how to access each part of that memory, etc. Generally speaking, there are two types of ISAs, 16-bit and 32-bit, most widely used. Obviously, there are pros and cons from each side. 16-bit means that you typically have, you will be like less expensive, and you can have, if all use 16-bit data, you have like smaller data, like a code size, compared to like a 32-bit. But 32-bit means that you are able to do like more stuff during every instructions if you're working with like larger numbers, for example. And 32-bit is a little bit more expensive, as you probably imagined. And the thumb2 ISA is hybrid, so it took a little bit good part from both. So it has the mix of both 16 and 32-bit instructions, and it consists of, and it's like highly optimized to be have a good trade-off between the code density, meaning the size, and the executing speed. And from like a higher view, so like we said before, different processors or different architectures can support different instructions. And if you just look at on the left side, everything underneath that is supported by the thumb2. So Cortex M, Cortex M4, M3, and just a theory of these instructions are all supported by the thumb2 instruction set. So the ARM v6-M architecture, which is what our Cortex-4 is based on, is, like you probably imagine, it's part of the architecture that will run on these type of instructions. They, let me just give you a quick, yeah. So how they do this, they have this different, so based on the different variants. Different variants basically means the CPU implementation of a specific architecture. So for example, Cortex M4 is a CPU specific implementation of the v7-M, and M3 is another variation. And they usually have some different hardware setups. For example, for the A architectures, when it's running the thumb2, it have this 13-stage pipeline core, and in our case, the -M, we have like a 3-stage pipeline core, which is much more straightforward, simpler, cost-effective, and also compact. So as we briefly mentioned before, so all the registers or like all the buses inside of the Cortex M4 are 32 bits, right? Or can you think of anything that, I guess first is why are people trying to do 32 bits and even nowadays some systems 64 bits rather than the good old 16-bit? And second, more importantly, why would people still keep the 16-bit code instruction set? Why were you able to do the 32-bit all at once? Let's do like a 1-minute brainstorm, and then we can chat with each other on the answers.
Well, yeah. You can do more with one instruction sometimes. I think you can process more data with one instruction.
Yeah.
And you can also like do for example, loading 32 bits from memory is one instruction instead of 2 loads of 16 bits into 2 16-bit registers.
Right. So you could get by with a fewer like clock cycles.
Sure, yeah. And then why use hybrid 1632? Because you want the code compactness of 16-bit, and you can use a lot of simplified hardware plus 32-bit for certain instructions that need bigger numbers.
32 bits.
Yeah.
All right, let's start with the easy one. For the question 1, any volunteers from the class? Yes.
We were saying like we need more access to more data, more memory addresses than before. So going to 64-bit gives you an exponential amount more data to be able to access.
Exactly. So with more bits, naturally we have more address that we can access for, and then we can just piggyback more memory spaces to the system. And we generally want that because it can do more things. One probably the things I want to add to that is by instruction itself, more bit on instruction, 32-bit versus 16-bit means each instruction has the potential to do more stuff. For example, if you add 16-bit together, we can't do that with a 16-bit instruction because half of those space needed to be saved for other flags and instructions, etc. So how about the second question? Anyone have an answer for that? Let's try a different person. Anyone have a good answer for the second question? Why we still need 16-bit instructions now that we already have 32-bit system? Yes. So we could, so that we can use the same instruction set for, I guess, more like legacy versions of the system, so we don't have to just get rid of them all at once. Yeah, I think that's definitely one of the considerations they did. Any other adding? Yeah.
I mean, code size is a big factor, especially for embedded devices where you are limited by a very small amount of flash memory. 16-bit instructions are smaller, so get more of them in a certain amount of space, but you still might need the flexibility of 32-bit instructions for certain operations.
Yes, very good actually. That would be the second major reason. So basically, the programmers, like you guys, you want all the good performance from the CPU core with bigger instruction bits, right? But you also want to have the option to have smaller code size for some specific applications or very specific devices. So this gives you the flexibility of both the better performance while also keep the option of having more compact, less code size to be possible. Yeah, it's just more detailed answers on the same thing. So next, we're going to move officially into the ISA. First, talk about the memories, registers, and data width, etc. Remember this figure? We're going to see this over and over during the whole class. So basically, the instruction are into the flash memory, and then the data, if you can see on the top. The instructions are saved in the flash memory, and the data are stored in the SRAM, and then they are interacting with the CPU core with system buses. And all those passes are all 32 bits bitwise. Although the instruction set can be 16-bit but all those paths are 32-bit because it's a 32-bit system. For this lecture, we're going to only care about the core and memory. So specifically, we will treat both the flash memory and the SRAM, in this case, as a unified memory space, just for easier, not only for easier understanding, but later on you will learn that all these additional stuff, including the peripherals and additional devices attached to the system, to the core, they all look the same to the CPU. They're basically a bunch of memory addresses that have exact same length of width of the data size. So let me give you a little bit on how just following what we're saying, like the memory organization. So for the system that we have, in theory, because it's a 32-bit system, it's supposed to have like 4 gigabytes of memory size. And those, instead of like some other devices that might have just everything from 0 all the way to top, and then you allocate based on where you're currently at, the whole address map is actually allocated by ranges. So if you look at the right side here, everything from 0x0 to 0x2, all that part is used for code. And then everything from 0x2 to 4, everything was saved for SRAM. And similar to that. And additional stuff are saved for the external RAM or external storage that you might need to or want to plug into the system. Notice that not all these addresses might physically exist. They probably just have that address, but does not necessarily mean that they have those physical transistors connected to them. Yes?
Yeah, just a quick question. So on the photo of the diagram,
This one?
Yeah. Is it pulling instructions one by one from the flash? That seems like slow compared to loading all of the instructions. Right? Or is it?
The instructions are saved in the flash memory, and then they are executed one by one through like the 3-stage process that we will talk later. So there's a fetch, and then decoder, and then execute.
So
Yeah.
so it's not loaded into RAM beforehand, like on a computer, like the program is not loaded into RAM first.
Okay, so I think you can think the CPU core, so everything in that green box, plus the memory, both memories, SRAM and flash memory, they are both computer, so to speak. So they are all together. Just some of these additional hardwares, for example, like keyboard or cameras, they are connected through additional connectors. But from the point of the CPU core, they all look the same to them. So in order to have these same instructions to access all of them, so nevertheless, it has to do this fetch to get the instructions somewhere. Yeah. And yeah, so all these regions are predefined for like code interpolations. Anything that that runs the ISA, the thumb tools, follows this exact same range definition. And this is actually the datasheet. If you look for our STM32, like the board you use in your lab section, you will notice that some of these, if you look at close on the right, and then we look inside of the SRAM part, you will notice that a bunch of them have these reserved space, which is, as we just mentioned before, they are actually not implemented. So, or they're called saved for future. So that's why they call it saved. These are usually for like cost efficiency because you can think of like ISA give you access to this big range of capabilities, but how many capabilities the manufacturer wants to implement onto each of the specific microcontroller design or system design, that's based on how powerful that chip is. So although all those boards have exact virtual, like fake memory addresses, not often are connected to actual physical slots or hardwares on board. Any questions on this? The fact that everything is just a memory address to the CPU, and for all the chips, all the CPU that runs on the same ISAs have this same exact memory allocation, or like memory predefined locations. You good? Okay. So, yeah, just like we said before, these are the ISA treats both of these memories as one unifying blocks, just like any other blocks. So the actual differences between these two, the flash memories and SRAM, is actually, does anyone know the actual differences? Okay, so the flash memory is the what they call non-volatile memories, which basically means that if the power is off, then whatever stored there still stored in the system. So that if you have like devices that you just connect to power and then automatically it runs, that's because the instructions are stored in the flash memory. And the SRAM, while it's like faster compared to the flash memory, but it's called volatile working memories. So anything that's stored inside of there going to be lost if the power is off. Okay. And let's talk a little bit more in detail on the actual memory addressing. So not much magic happening here from the bottom to top. The memory address got increased all the way until 32-bit. So, and each memory location holds a byte. And the way that we like you to think about this is because just, we have a 32-bit system, so you can just think of them increased by 4 each time instead of have every time, listed as the byte by byte. You can just think of them as a 4-byte increment every time. Both because all the buses are 32-bit in the system. And the key important thing here is the Indian, the big Indian versus small Indian. You guys should probably already learn these. So basically, small Indian have the base address stored at the least significant, and then the big Indian have the base address stored at the most significant. And in our class, if there's not specifically said, we assume little Indian for all other questions, exams, etc. But in the Thumb 2, they actually support both, and then they have like they can implement that switch, a flip on the fly if you need it. And those are from like the memory side. If we look into the CPU core, these are the part in the CPU that they use to interact with the memories. These are the processor registers. Again, they're all 32-byte, and they are some general purpose registers, the R0 to R12, that they usually call like general purpose registers. And then there are some special registers, usually from like R13 to R15. We don't have to learn the details about them just now, but we will talk more about them in like later lectures. Basically, R13 is for like stack pointer, where you're in the stack of the instruction. The link register tells you where you're supposed to return to, if there is a subrouting function calls, etc. And program counter is just, keeps track of what's the address of next instruction inside of your memory. And there are some other bunch of even more special registers. And for now, we don't have to learn too much about them. So now that we look at both from the memory side and also from the register side, what happened when there is a code, going on? What happened exactly between the core and the memories? So this on the left is the example of a C code that does pretty normal things, and these things color coded will be saved under the SRAM because the coded, the parameters and stuff, they'll usually be saved under the SRAM because they're data, and then the blue part, which are basically the instructions, will be saved as the flash memory, which is coded as blue there. One different thing here is if you look at that gray part, that little integer I that used for the loop. So basically they, because there's some like internal optimizations for performances, usually the compiler will just save them doing it inside of one of the registers rather than actually put it onto the SRAM for like just faster executions, etc. I think one of the classmates mentioned before, how if we can do this faster, this is one of the compiler optimization that will allow you to execute some of the code faster just by keeping it inside of the register rather than have it inside of rather than in the memory. You will learn later, that basically saves you like one instructions. Otherwise, you have to load the data from the memory first and then execute. Does that all make sense so far? Any questions? Any questions on how every part of this piece of code is stored? And okay. So, pretty quick recap. We have the unified memory on one side, outside of the CPU, and we have the processor registers on the other side, which is inside of the CPU, and they interact with each other and then do all the performances or like instructions that needed. From the memory perspective, it's byte addressable, so anything in a byte, and then we increment it by 4 by default because it's a 32-bit system. Cool. So next, we're going to talk more about some specific instructions, how the encoding happens, and arithmetic, logic instructions, etc. You guys should probably remember this, but just by looking at if say we have like 2 instructions and move as R0 on number 10, and can anyone tell me what this does from your 370 class or any of your self-learning experiences? Or what's the hash means in this case? I mean, I'm sure you guys all know this, right? Okay, so the hash basically means an immediate. And if we want to look at these instructions, and then on the bottom is the architecture reference manual, which we will provide in any of the exams, and you can find those for your homeworks and etc. This way, we are able to find what's basically decode from the instruction assembly code to what the machine code looks like. In this specific case, the move as meaning 001, which is 001, and 00, which are 2 bits that just putting inside of that instruction. We will talk about that in later lectures. And then on the end is basically the value 10. Similarly to the and then they will be saved. They will be saved to this memory address. And this memory address is just where the flash memory, where the instructions are stored. The address there, the actual number might be a little bit arbitrary, depends on where the system is at, but it will basically try to put the instruction at that location. And similarly for the second, you just decode it based on the cheat sheet, and then you will be able to come up with the actual machine code. The interesting thing here is sometimes it will do this auto optimization that store both of these instructions because they are 16-bit instructions into one 4-byte memory addresses. So, yeah. Does this make sense to everyone? Is it too basic, or is it like I'm getting no impression from everyone? Is it all good? Yes.
That's how it works with the 16-bit and like, does it signify which one is using for the program?
That's a very good question. So we will get to that in a few slides later. Yeah. So, now that the machine code is being, you know how the machine code works. Basically, we internally inside of the CPU, we have a program counter, which is one of the registers that we just mentioned before, special registers that keep holding the memory address of what's the next instructions that are going to be fetched from the memory to the core. Just everything, it goes with this 3-step. We fetch the instruction based on the PC address, and then we decode the instruction, and then we execute the instruction. And this will be like a typical pipeline. Yeah, just every time the instruction by default add to another address, typically 4 byte, and then just keep executing unless there is a subroutine or function calls happens. And this is what happens when there is a 32-bit. There is like all the instructions are 32-bit instructions, so the pipeline fits perfectly. But if we do have 2 16-bit instructions, what happens is it will just wait for the second 16-bit on that, and then essentially adding one stage and then execute them together. But just like one of our classmates brilliantly pointed out, so when the core fetches the next instructions, how does it know it's actually one 32-bit instruction versus it's 2 16-bit instructions? Let's do like a 30-minute brainstorm on this, and then we can all share the answer.
Specifically, if you're switching to
What's that?
thumb is aligned to an odd address, thumb is aligned to an even address.
But that doesn't matter. Like within thumb.
Yeah, I don't know within thumb how it does it unless. Yeah, but I know like Cortex A's switch between ARM and thumb by switching the alignment.
Like
知道吗？知道吗？
32-bit instruction is just short.
Yeah, it could be like a low bit. Yeah. Or maybe it decodes the first half and then that gives it a
Sometimes it's better for
say, hey, we need the second half.
All right. Anyone wants to share your thoughts? Anyone? Yes. Sorry, guys. All right. Good. So it will be like a piece of a few bytes somewhere in the instruction that tells you whether it's a 16 or 32.
Full 16 bits would be like maybe half. And then it would look at the next.
I see. I think that's one way to implement it, but that also means that we wasted 16-bit of the memory space, which is if we look back to here, if we have like 2 16-bit instructions, they actually stored in one 32-bit 4-byte locations rather than separating two. So that's one possible implementation, but that's not how the Cortex-M, not how the Thumb 2 implemented it. Any other guesses or any other method? Yeah, on the back. Yeah, I think that's pretty much how they implemented it. Obviously, there are different ways of doing this. The way that they end up doing this is just to have a couple bits in the lower bit, so that when you look at it, you are able to break two and then look at the first 16-bit first, and then the second 16-bit. They specifically implement this 5-bit to be an indicator of whether this is a 32-bit instruction or 16-bit instructions, by just quickly checking on that. There are obviously different ways to do this. You will learn later on, like way down in the lecture, like why these bits are being chosen. But so far, just know that a small portion of those 32 bits are used for these purpose to determine whether it's a 32-bit or 16-bit. Yes?
Does that mean that there will be a whole second cycle dedicated to fetching the second instruction? Fetch 16 bits? Or
So the fetching part will actually just be done once. So we fetch the entire 32-bit or 4-byte at once. And then if, when it's decoding, it sees that this is the two 16s, they basically decode twice. So the fetching just happened once.
okay, so fetching might happen once for two different instructions.
So yes. So if you look at this
Okay.
figure here, basically the fetch happened at the same cycle, and then but it takes one additional decoder cycles to decode this instruction because it's two instructions. Any other questions regarding this? Yes. What if there is only one instructions? That's a good question. So the compiler will probably maybe they fit all the FFFs in there. That's totally possible. Yeah. That's just how the compiler optimized for the space and all that. Any other questions? Okay, cool. And then let's give you a little bit exercise, and we can look at these together. So just based on the following instructions, which type of encoding we should use. T1 versus T2. T1 is basically a 16-bit, and T2 is a 32-bit. How about this instruction? We want to put a value 15 into the register 3. Should we use this a 16-bit or 32-bit instruction? Anyone? Just shout out the answer. 16, and why is that? Very good. So if you look at the top one, that's how the 16-bit are allocated for each of the instructions. The bottom 8-bit, total enough to hold the number 15, and then the RD, which is the address for the registers, they also fits the R3. 3. How about this one? Anyone? Yeah. 32, and why is that? Yes, very good. So if you look at the 16 version, there's only 3-bit allocated for the register address. So anything goes beyond that has to go through 32 instruction, which they are called upper registers. How about this one? So 32-bit, because obviously this exceeds the 8-bit for the data, like the space to fit on the data on the 16-bit. This is all look good to everyone? All right then. So here's a question for you. So how does the ISA make a distinct between the low and high processor registers, and how does the instruction size impact the use of low and high registers? It's just, I think 20 seconds, we briefly touch on this, but yeah.
Because the number's bigger than 6.
No.
Oh, because that's a convenient distinction of which can be
可以看一下图片吗？应该就看这个图片吧。就看这个2D，然后超过8就不能存进去了，就在这32。
All right, anyone? Anyone wants to talk about this? Let's try some other people as well. Anyone else? Anyone from the class? I hear a lot of discussions. Yes. Yes. So if you use higher registers, that basically forces the core, or like forces to use the 32-bit instructions. But if you use the lower registers, it can be implemented on both 16-bit and 32-bit. Can anyone quickly think of any other method if you want to force this instruction to be 32-bit? Any other method you could do? Yeah. I guess that's one way to do this. Not very common because the flipping is actually happen on the fly. So even as long as you know whether it's a 16-bit or, yeah, like if you use Little Indian versus Big Indian, doesn't necessarily guarantee you if it's a 32-bit or 16-bit. But another method we mentioned, we show it here. You can also make sure that the data you have is exceeding the 8-bit range, so that it forces you to a 32. And if it exceeds the 16, well, if it exceeds even more space on the 32 instructions, then we will use a different type of instructions, which we'll talk about in a few slides. So generally speaking, these are types of assembly instructions, or ISAs types that's supported by the Thumb2. We have the arithmetic and logic ones. Like, I think these will probably be the most familiar to you guys: add, subtract, multiple, and divide. And we also have the data movement, load, store, move. The load and store are usually used to interacting between the core and the memory, and the move are usually used for the instruction that's within the CPU core, like moving values around registers, etc. And there's some like compare and benches. It tells you if there is a condition being triggered, and then the instruction go to a different address, etc. And some breakpoint interpolations, those ones, we don't have to look too close to them just now. So, just give you some common instructions. So these are menus, or like a data sheet of the instructions that will be provided to you during exams and stuff. So please do not remember exactly what these these things does. You are able, just like one Google away, or even during the exams, you should be able to find them on the exam we give you. And these are commonly used arithmetic operations at just the ones that we mentioned. And also we have the multiples, divide the S bit that have the S suffix that have a lot of the instructions. They stand for like updating the LU flags, which basically means updating the condition flags, which are some of the flags that are saved in the special registers. And to just give you a little bit more information, the flags that we have, typically ones you will interact with is just like N flag, Z flag, C flags. The N flag is negative flag, whether this result bit is, is actually negative, or it's just pretty big and almost exceeds the entire range because it has a 1 in the top most significant bit. And then the 0 bit is just set if the result is 0 on that specific register or any registers. The carryover bit is, like we said, if you have like a add, for example, add instructions that go overflow the number of bits that you currently have, you use 2 instructions, and then you have this add C or ADC that used for using the carryover bit from that register. Yeah, this is just like more details. Again, these will be all given to you during as like data sheet, and give you like a little bit more information, just like how the carryout works. If we have like more than a bit of data, and then that 1 bit will be set as a carryover bit in these instructions. We also have some other let me see. One other interesting instruction here. WNB, the move not. It basically it's a instruction that takes a value, which in this case 0, and do like a bitwise not operation. So what happened here is it gives like a number 0, but in the actual register is stored all Fs. So just a faster ways to give like all Fs to the register. Otherwise, you will need like a 32-bit instructions for sure to do that. And we also have some bitwise logics, like the one we just showed you, like the one on the bottom, the move not. We also have like bitwise and, or, etc. The pretty standard bitwise operations. And give you an example on bitwise or. So if we have like two registers, like from R0 and R1, and then we're trying to basically store that value onto the R2. This is what's going to happen. You look at specifically those bits. Well, you look at the two register bit by bit, and then give like a OR operations, and then store in the R2. Why do we need bitwise operations for our system? Can anyone make a quick guess? Yes. Yeah. But like, any specific applications you can think of that requires this type of masking, for example. Yeah, that can be true. Yeah, if you have like so if you have like a GPIO that was connected to various different things, and each one bit may be connected to one thing you want to trigger, then you might want to operating some bitwise operations so that it only turns on certain flags without interfering with whatever else is happening. So yeah.
You use bit masks as operations to implement state change.
Mm-hmm.
So like state transitions and so bit masks.
For like faster operating
Yeah.
speed. Yeah, that's true as well. So yeah. Cool. And we also have this BIC, basically means bit clear, and it clears the lower bit of that register. In this case, it just gives this operation, and then on the register 2, the lower 4 bit will be cleared to 0. This is again, because we're interacting with embedded systems. Sometimes every bit can matter. It might corresponding to a thing that's corresponding to one operation or one event that needs to be triggered or untriggered. So yeah, the bitwise operations can actually be quite handy for those scenarios. We're good on the logic and arithmetic operations. So let's move on to the move, load, and store. Okay. So yeah, the move, like we said, there are different ways of moving data between register. Move, these functions are usually the ones that are used for register movings. And move not instruction, like we just said, does like a bitwise logic not. And we have these move immediate. Let's see. So this way, so if like the move immediate basically used for adding a constant to move like a constant value or store a constant value into your registers. So this way you don't have to load the value from the memories, etc. And it typically make it faster because it saves another additional cycle of load from the memory. And if we want to load a 32-bit number into a register, then we have to use what they call like move wide and move top. So these two operations, basically the move wide does not affect the lower bit, and the move top does not affect the lower bit. Move wide clear the upper 16-bit. So for these type of instructions, the order of you implementing them actually matters. You should basically, make sure you, in most circumstances, do the move W, move wide first, and then do the move top. All good? Just like different ways of moving data and interactions between the registers. And then it's going to be a little bit more interesting. So we are going to the memory side as well. So for the memory side, I would be load and store. Those are the two main type of instructions you will need from interacting between the CPU to your unified memory space. And let's consider this one instructions, load R3 and then bracket R1. What it does is it basically take the value that's stored in the register 1 and then use that as the memory address and then load whatever data that was stored in that memory address and then load that into the register 3. I hope this all seems familiar to you guys if you take 370. So we're good. Okay, and we also have like different versions of load and store, for like, yeah, you can just read yourself, but 8-bit, 16-bit, have word, etc. So, and how the memory stored is basically used to better like for the memory organization, and you will notice from the previous slides here, certain type of operations, for example, the have word, it has only been implemented for the load, but it's not being implemented for the store. And any guesses why that's the case? We can just shout out answers. We don't have to actually discuss. Anyone want to make a guess why the store is, why the load has, I guess, looser control, looser restrictions compared to the store? Anyone? Yes.
Because the register always has 32 bits, so it makes sense
I think mostly it's not because of that. So actually, mostly it's because when you load from the memory, you're not changing anything on the memory. So it's kind of okay that you want to load from any address that you want. But when you do like store only have, then that might crop any of the existing memories. So these are typically not allowed. So that no data was cropped during the operation. And we have, okay, cool. Let's look at this example, actually. So we have this one instruction, and that's the value that's currently in the register 0. What happened when this instructions is supposed to happen? Well, the program will basically look at the address that's being stored in the register 0, which is that, and then look at what's being actually in the unified memory space, what's the data is being stored in that location, and then take that whole thing and load it into the R1. Little Indian, so we have that number in the register 1. This hopefully is all good, and we have various different ways to do this. We have this offsetting addressing that basically it happens is it does a immediate offset on the fly. So when they look at the data that's stored in register 0, immediately add 4 to it, and then look at that value, which in this case will be A004, and then load that value into the register R1, which is dead beef. And what's important here is with these instructions, the offset happened on the fly and does not change what's currently was or previously stored in the R0, register 0. But if we do this a little bit, like the prefixing on the addressing, what that happens is it just the increment immediately before the actual load instruction, and also change on the register value. And then it goes to that, and then load the same data. But notice that the value that's stored in the register 0 is changed in this instruction. This is pre-indexed addressing. We also have post-indexed addressing. So if we have the number like 4, here is because just it's 32-bit, 4 byte ahead, just like we talked before. We can always think about things increment 4 byte at a time. So this essentially means that it would go load from whatever is currently stored in register 0, does not do anything to the number, and then load the data, store that in register 1, and then does the increment. And these are usually used for like different types of loops. Sometimes it can be like more efficient in code. And you will also notice this performs similar to what the program counter does. So every time just by default, it increases 4 on the instruction register, instruction address. Any question on the pre-indexing addressing versus the post-indexed addressing on the load? Okay, so cool. Give you like a quick summary. This can be quite handy. If there's no index, just pretty normal. Data got loaded, and whatever value stored in the register does not change. Pre-indexing, you do the address increment, data increment on the fly for the addressing, and then you look at the increased address data, load that, and then without changing of whatever in the register value, if you do that pre-index with update, a little additional sign, then you update whatever the value in that register as well. And we have the post-index, which does a similar thing to the no index, except that it increments whatever in the register 0 in this case by 4, or changes the value in whatever the addressing register is, the value in that. Does this all look good? Okay, cool. So here's a question for you. For like a load instructions, what's the largest possible offset that can be achieved with an immediate? And mind you, that on the bottom, which is like a bitwise allocation for a for a instruction. Let's take maybe 30 seconds on this, and then we can look at this together.
Oh, that's a good question. I don't think they do negative attack.
Yeah, because it says immediate prediction equals to offset, so it would be
Yes, that is, yeah. So you
Yes, so it would be that. I just want to understand a couple of the instructions.
Yeah. A lot of the stuff I'm a little rusty on. Way better than I thought.
Anyone? Based on the data sheet you have, what's the largest amount of immediate increment, or you can achieve? Anyone? Yep.
Would it be 2 to the 12?
Yeah, very good. It will be 2 to the 12 minus 1. So hopefully that's, because the bits allocated to this value is only 12-bit here. So that's the largest value it can increment. We have like 0 to 2 to the power of 12 minus 1. That's all clear? Any questions regarding the move, load, store, how the values got moved around within the CPU core, and also how the data got moved between the CPU and the memory? Yes?
So this is a signed number?
Which one? Oh, for the immediate, yeah. Any other questions? Yes. Oh, I see. I think it's 2 to the 12 minus 1, yeah. Yeah, it's, that's a very good question. I don't think for the increment immediate, it's like a signed version. I think it's unsigned. I'll double check on that, but I think it's unsigned for that, yeah. Any other questions regarding the move, load, store? Okay, cool. And then we will move on to the next part, which is the flow control and branching. On the branching, these are like the, I guess, most widely used instructions. It's usually just the B is unconditional branching, and then BL is branching with link, which means that link and L stands for the link register. Basically, it tells you branch and also tells you what's the supposed address or like a different subroutine is supposed to go to. And that link register typically store a different memory address where this subroutine call directs to. And for the BLX and BX, it's just, branch to the address that's stored in different specific special registers that we mentioned before. Remember, like the R0 to R12 are the general registers, and the remaining registers are special registers. These are a lot of those special numbers or special addressing are stored in these registers. The link register, namely R14. And these are more, just give you even more details on the conditional codes, and then branch plus condition. Hope these are all look familiar to you. If not, we provide all these in the data sheet, and then you can refer to them during exams and stuff. So, let me give you a quick example on this. Usually, it's if we do look at the comparison. Oh, sorry. The previous is for branching. Branching meaning usually it's from whatever your current instruction to a subroutine. Sometimes a subroutine is just right after the current addressing. That's if you can think of like a if loop, and then one of them goes directly to the address below that, the other one got subroutined to a different address. So these are all possible, and the comparison is what actually happens when they do these compares. And you have different type of compare, and then all these instructions by default will update the special condition flags by default. So you do not have to add the S suffix for these comparison instructions, as opposed to previously add, subtract, move, etc. You need the one additional S sign suffix for updating the condition. I hope, does that all look okay? Okay. So these are just a quick recap on the different type of instructions that we talked about. Arithmetic, logic, move, load, and store. Move, load, store tends to be the most confusing ones, as well as some flow control and branching. And then next, let's look at one of the example together. So let's say we have this one C code here, and then assuming X in this case is a 32-bit integer stored in the memory. What this will do is it will be converted into this 3 line of instructions, and basically load, and then add, and then store. Does this have any question to anyone? Like why one line of code got transferred into 3? Okay, I assume everyone understands, but just to re-emphasize, if whatever number is being stored in the memory, you always need to load it first, and then if it's being stored in the memory, you do the store, and then all the operations in between happens within the registers. So that's just from like the very assembly side. What actually happened in the register and the memory is, well, first we have the program counter, which fetches and decodes the instruction. The program counter points to this current address, and then that is the machine code number that was represented for the load R101. And you don't have to remember this, but if you look at the data sheet, that's what the machine code is represented. Remember at the very early in the slide? Let me just show you. Remember, actually, never mind. Can't really find that slide anymore. But yeah, so that's what the instruction, the load R1, R0 for. And then after that's happened, we'll basically look at whatever the value that was already currently in the register 0, and then look at the memory address, and then load that number stored in that memory and value and into the register 1. This should hopefully be no question for everyone. So what happened next is the add, basically the x equals the x plus 1, and the program counter by default incremented by 4, and then look at this instruction that's saved in the memory, which corresponding to that instruction, and that basically triggers a add function in the LU to take whatever number in the register 1 and then plus 1 immediate, and then store in the register 1. So notice that register 1 was updated from 02 to 03. This is all good? You will run into a lot of these like practice questions in homework and in the midterm exams. So, And then after that, we basically store the x back to the memory, which again the program counter incremented by 4 and then point to that, and then the machine code was decoded into the store R1 register 0, and that number got stored in that corresponding address to 3. Any questions on this? Yes.
This might be a silly question, but you said the program counter is incremented by 4 each time. Isn't each one of these a 16-bit instruction?
Yes, they can be 16-bit instructions, but every time it's 16-bit instructions can be also written into a 32-bit instruction, depending on how the compiler works.
So it just wouldn't necessarily always make sense to say reading the second half of the 32-bit as an instruction.
You always read that, but in this particular case, the second half does not have those 5-bit as the flag, showing that it's a 16-bit instruction. It is a 32-bit instruction. And also, I think for the address add, so yeah, so these are all 32-bit instructions. Any other questions regarding this example? Okay, cool. So in the spirit of giving you some heads up on the lab kit, and then you don't blow up any of the lab equipment, there are different type of connectors, and they are female types, male types. Make sure you do not short circuit anything. A very easy way to check that is use a multimeter. If you guys all use that, just place into the continuity mode and then test whether of the two pins are connected. And you should not, you should only connect connectors that are the same type. If you're trying to connect, say, like a battery special connectors to like just a random jumper wires, that might cause some issue with the batteries, especially the Li-ion batteries nowadays. And to give you a quick recap of the today, so we talk about like the ARM, how the architecture and the instruction set works, and the ISAs. We talk mainly, if you have to remember one thing, how to interact between the CPU core and the memory through load and store, and if you want to do any of the operations within the registers, usually through move and also some other arithmetic operations like add, multiple, subtract, etc. And the registers are basically the core part within the CPU core that used to store any of the values that needed for immediate operations. And then typically we have 13 general purpose one and a few other special ones. The ones we looked at are program counter, linked register, and then some of the control flags, zeros, overflow bit, and all that are also stored in some of the specialized registers. And we also look at these instructions in more detail. So, any questions on today's lecture? We have one group exercises that we had for this, but I don't think we have time to go over this. I will post the answers to the slides. So it will be 2 slides files on the Google Drive, 1 redacted and 1 post lectures. So cool. Yep, that's it for today. Thank you for coming.
Yeah, I do want to ask you about I want to ask you about lab.
你学 CS 的还是 CE？CE， 你学 CS？ 我是学 CE。CE
Is it really loud?
因为我们那个交大，上海交大是双学位，挺厉害的。上海是排名第3吗？差不多第3、第4。在上海，如果想留学，成绩得要多少分呢？
留学就是我们学院300多人，
300多。
就是选100个过来这边，但不是所有人都会选择过来这边上学。
要不要加个微信？
Yeah.
I did take it last semester, but like I already forgot most of it.
Yeah, but I took it 2 semesters ago. I'm like, I have to do all stuff. Are you still doing the double major?
I don't think I have time for it the moment.
Are you just doing this kind of hard right now? Yeah. All the classes are you taking?
215, 281.